Excellent. Welcome everybody. We're gonna do a quick lightning talk on integrated graph machine learning with GDS 2.0 and Python. So quick introduction. So my name is Sean Robinson. I am the lead data scientist at Graphable. So at Graphable, we're kind of a one-stop shop for all things graph related. So if you have a graph or are building a graph and you want to do anything with it, we do everything. So whether that be building or rebuilding a backend application, visualization, BI type work, or personally what I do, which is graph ML and analytics. If you've got a graph, we do stuff on it. So I'm a self-proclaimed graph ML junkie. I am a graph educator at the University of North Carolina at Charlotte, where I teach network science and Neo4j. And I'm an avid Avatar: The Last Airbender enthusiast. If anybody wants to talk about Avatar later, please hit me up. And with that, we're going to go ahead and get started. If anybody wants the code from today, it will be on my GitHub at Sean K. Robinson. So feel free to clone my repo and pull down the code. So we're going to go ahead and get started. Oh. Cool. All right. First thing I would do is recommend, if you are going to go through this, to check out the brand new, very shiny GDS 2.0 Python driver that Alicia gave us a sneak peek of this morning. This is something that I've been very excited for over a year now, to be able to really bring all of the power of GDS natively in with Python, because as data scientists, we are not engineers per se, but we want to work in the tools that we work in. And so one of the things that I'm very excited about this driver is lowering the barrier to entry for new data scientists who are learning Neo4j. So the last thing I want to do when I'm trying to get a data scientist excited about Neo is tell them that there's a whole bunch of new stuff that they have to learn, because that's going to really quickly kill the vibe. So we want to make it very, very easy to get people up and running using the platform, but without having to know a whole bunch of custom stuff. So with that, I'm going to run through this library or this notebook and kind of talk about it one by one. Cool. So I'm going to do my imports, and then I'm going to establish my GDS object, which is like my driver. And then today we're going to be looking at a supervised classification use case for one of the standard benchmarking data sets, which is the Quora data set. So for those of you who are not familiar with Quora, it is a citation network of ML papers which are related to one another. And so here you can see kind of a rough diagram of the data. And then this is ultimately where we want to get, right? Where we are separating our data into separate spaces and then are able to classify the papers accordingly to their labels. So all this data is from Claire Sullivan's it's hosted on her GitHub. Thank you, Claire, for hosting the data for me, so I don't have to. And we're going to start diving right in. So this will not be as wicked cool as what Alicia did today. This is going to be pretty straightforward. I'm just loading in the data. So right now I've created my constraint to limit the IDs within my database. I'm bringing in my nodes. You can see this is a relatively small graph, about 2.7 thousand nodes. Bringing in my edges, another 5,000 edges. So now we're in to actually generating my underlying projection. So this is one of the things that I really love about the new driver, which is my ability to create what is a projection object. So previously, some of you might have engineered this by hand, where you're essentially creating a string and then doing a graph.create call. So now I can just use my graph.project function, pass it the objects in question, and dynamically update those if I want. So I'm going to run my projection and create that. So now I have this super helpful graph object stored in my variable g that I can now do cool things with. So I've created a quick little helper function here that just kind of prints out a couple of the summary stats that are included on my graph object. So here you can see I have, the name of my projection, I have my degree distribution, I have the density, node count, relationship count, and all of that is built natively into the graph object. I don't have to write something that is going to return those statistics. I can just call it directly as a method or a property. Cool. So now we're going to get in the actual GraphML part of things, where we're going to utilize FastRP, again, much like we saw from Alicia today. But one of the things I want to highlight in this talk is how much the new driver integrates seamlessly with the workflows that we are used to using as data scientists. So I don't know about you, but as a data scientist, if I run something and you give me data back, it better be in a pandas data frame. If it isn't, I'm going to be unhappy. So that is my expectation if I'm using Python and data science, is that we're going to be using that as our standard lowest common denominator data structure to be able to manipulate my data, and that's what we're seeing here. So one of the things I can do now is use now that my data is in a pandas data frame, I can use all of the normal transformations that I already know that are native to pandas to start transforming my data. So here I want to unpack my columns. So here I have 64 embedding dimensions for my Cora data set. So you can see here I have my node ID, and if I scroll over, we have 64 embedding dimensions which represent my graph, okay? And this is in my nice, pretty pandas data frame. But what I want to emphasize is that this now behaves like any other pandas object, and so does the data which is returned from our run Cypher function. So GDS has a very convenient run Cypher function. If you've used the previous Neo4j driver, you have to deal with things like sessions, open, close, all of those things. We really want to extract those things away from the data scientist. We don't care about those things. We just want to run Cypher and get the results. We don't want all of the session and having to deal with that. So GDS.run Cypher returns my results in a pandas data frame as I would expect. And because I know that, I can use it in my merge function here seamlessly with my previous data frame. So what I'm doing is I want to get the labels of my data, because right now I don't have my actual y variable, and I want to bring that into my data set. So now, because I know it's going to return as a pandas data frame, when I run this, I already have my class object natively populated into my data frame. And when you look at this, this is now, if you're familiar with generic kind of ML pipelines in Python, this is starting to look like a typical ML data set that you might use with scikit-learn and stuff. Spoilers, we're going to use scikit-learn later. So now I might want to further enrich this data. So for those of you who are familiar with ML workflows, something that's very common is that we generate statistics in the graph, and then we feed those to a traditional classifier. So I've done that up front with my FastRP embeddings, but now I want to further enrich this with my PageRank and my betweenness centrality measures. So I don't actually need to call them individually. I can actually use my getAttribute function, because we're in Python now and I can do that, and I can simply loop over the statistics which I want to collect and aggregate. So when I run this, it's going, again, because I know that this will return as a pandas data frame, it's going to run it, return it in a data frame, join it to my data, run it, return it in a data frame, and join it to my data. And all of that I can do in just a couple lines of code. This is not the kind of thing I could have done without this driver, or if I was to do this, it would have required a lot of F strings and formatting and a bunch of junk that honestly wouldn't be worth it. But now I have my PageRank and my betweenness stats natively present in my data frame. So now this is essentially my, my data that I'm going to work with. This is my X and my X's and my Y. So now that I'm in pandas, I can do all the normal data science things that we might want to do. So I can start using some of the native functions within pandas to start doing things like producing box plots. And so here I can actually see that there are actually some interesting statistical outliers. So if I want to take a deeper look at this, I can use, again, all of my normal functions. So I can say, df.sortBy, or sort values rather, and we'll say by betweenness. Let's make sure they are descending. And I want, let's say, top 5. Cool. So now this has already ordered my data frame. So now if I want to investigate these outliers that we can see in my box plot, I can automatically pick those out, and I can see, okay, what classes are they? And I can actually see, okay, my top 5 are pretty much all different classes, which might be interesting to me for whatever reason. And it is not that this is particularly fascinating. It is that since I can do this, there are about 25 other things I can do. I can also take my data that I got out of Neo4j and feed it into other Pythonic libraries. So now I personally really like Seaborn for a lot of my visualizations, so I can start generating visualizations using Seaborn, so I can actually visualize, this is my PageRank variable in a histogram. And then I can even start to visualize my embedding dimensions. So if I want a visual representation of how well I have embedded my data, I can create a TS&E plot and start to visualize the actual embedding dimensions in a 2D space. This will take a second or so to run. And now I start to understand what my embedding dimensions kind of look like when compressed to 2D space. So I can see, my green class over here and my purple class and my blue class are fairly well clustered. Looks like my red class is kind of sparse. So we'll see what kind of results we get from our classifier. But once again, this is just one more way I can seamlessly start to pull data from Neo4j and Graph Data Science and start integrating it with my normal ML workflows. So now everything from here on out is what we would generically expect from a scikit-learn ML classification use case. So I'm going to start by encoding my labels because I don't want to have my label be neural networks. I want it to be a 0 or a 1. And then I can start doing my train test split. So now I'm doing a 30-70 split here. So now I have X train, X test, Y train, and Y test. And now in this case, while Neo4j and Graph Data Science are nice enough to offer logistic regression and random forest natively, which are great models, I might want to use other models that aren't natively supported by Graph Data Science. In this case, XGBoost, which is one of the best classifiers we have today. And so if I want to utilize the power of XGBoost, this lets me very, very quickly get my value out of my graph into some kind of embedding space and then pass that on to a model I wouldn't have otherwise had access to in GDS alone. So I'm really merging the skills I already come to the table with as a data scientist with the features that GDS offers to me. So now I can train my XGBoost model to run my predictions, and now we can start evaluating. So let's see how we did on accuracy. 81, not terrible, not great. I can start creating confusion matrices, so start evaluating how my data performed and which classes I might be struggling with. And I can start looking at my feature importances to start see, okay, which of those embedding dimensions contributed to my classification and my underlying model. So here you can see my 60-second dimension contributed the most, and there's a pretty smooth curve. And another interesting thing to note here is that my page rank and my betweenness are not present in this top 20 list, which tells me they might not be providing that much information. So this gives me feedback as a data scientist to perhaps go back and rerun my hypothesis and start to understand better, okay, what do I want to reevaluate? Do I want to exclude those? Do I want to change up what algorithms I'm considering? So that is the extent of what we're going to be looking at today. Questions from anybody? Again, all this code is available on GitHub, so please, if you want to clone this, feel free. But yeah, anytime for questions.